There is a field in Canada covered in 2 feet of snow. Nothing moves on the surface. Nothing is visible. Nothing makes a sound that a human ear can detect. A great grey owl sits in a pine tree at the edge of the field. She is completely still. Her face is turned toward the field. Her eyes are not moving. Because she is not using her eyes. She waits. Then she drops. Not toward anything visible, not toward any movement on the surface, not toward any sound a human observer can hear. She drops toward a specific point in the snow, hits it wings first, punches through 60 centimeters of frozen crust, and pulls out a vole. She was right. She is always right. The vole had been running through a tunnel under the snow, silent, invisible, completely undetectable by any human sense available to a predator standing 20 meters away. The owl detected it, not where it was, where it was going. She calculated the vole's trajectory from the sound of its movement, sound traveling through snow at a speed different from sound traveling through air. And she aimed not at the source of the sound, but at the point where the vole would be by the time she arrived. She hunted something that didn't exist yet. This is how she eats, every night. This is the story of the great grey owl, the animal with the most sophisticated sound processing system ever measured in a living creature, and what the science of her hearing reveals about the nature of perception itself. The face. Before the science, the face. The great grey owl's face is its most extraordinary physical feature, and not for the reason most people assume. The facial disc, the large, flat, circular arrangement of feathers that gives the owl its distinctive appearance, is not decorative. It is a sound collection system. The disc functions as a parabolic reflector. The feathers are arranged in concentric rings that channel incoming sound waves toward the ears, amplifying and focusing them the way a satellite dish focuses radio waves. The disc can be adjusted. The owl controls the shape of its facial disc through a complex set of small muscles, changing the curvature to optimize sound collection for different distances and directions. When a great grey owl turns its face toward a sound, it is not looking at the source. It is aiming its sound collection system at it. The ears themselves are hidden beneath the feathers on either side of the disc, not at the tips of the ear tufts, which are purely decorative, but asymmetrically positioned on the skull. The left ear is higher than the right ear, not slightly higher, significantly higher. The left ear canal opens upward and to the left. The right ear canal opens downward and to the right. This asymmetry is the key to everything. The asymmetry. When a sound reaches a great grey owl, it reaches both ears, but not at the same time. If the sound comes from directly ahead, it reaches both ears simultaneously, 0 degrees, directly in front. If the sound comes from slightly to the right, it reaches the right ear a fraction of a second before the left. The owl measures this time difference and calculates the horizontal angle. If the sound comes from slightly below, it reaches the right ear, which faces downward, slightly before the left ear, which faces upward. The owl measures this and calculates the vertical angle. The time differences involved are almost incomprehensibly small. Maximum horizontal time difference, approximately 200 microseconds, 200 millionths of a second. Vertical discrimination, differences as small as 30 microseconds, 30 millionths of a second. The great grey owl's auditory system can detect, measure, and process a time difference of 30 microseconds and translate it into a precise three-dimensional coordinate in space. No human-made sonar system operating passively without emitting a signal can match this resolution. The owl does it with biology, with two holes in the side of its head positioned at slightly different heights. The 3D map. The auditory processing doesn't stop at measuring time differences. The owl's brain takes those time differences and constructs something extraordinary, a complete three-dimensional map of the sound space around it. Not a flat left-right representation. Fully volumetric, above, below, left, right, near, far, a spatial model of the environment built entirely from sound, updated in real time, accurate to within 1 to 2 degrees in both horizontal and vertical dimensions. Studies of the owl's auditory cortex have found that it contains a physical map, neurons arranged spatially to correspond to actual positions in space. A sound from the upper left activates neurons in one specific region of the auditory cortex. A sound from the lower right activates a different specific region. The owl's brain is literally a map of the world organized by sound. In darkness, in snowstorms, through 2 feet of frozen material that would block every visual cue and muffle every sound to inaudibility for any other predator. The great grey owl hears through it. The calculation. But the 3D map is only the first part of what the owl does. The second part is where it becomes something else entirely. A vole running through a snow tunnel is not stationary. By the time the owl detects the sound, processes it, constructs its spatial map, drops from the tree, crosses 20 meters of open space and hits the snow, several seconds have passed. The vole is not where it was when the owl first heard it. The owl knows this. Studies using high-speed cameras and GPS tracking of both owl and prey have documented something remarkable. The owl does not aim at the source of the sound, it aims ahead of the source. It calculates the speed of the vole's movement from the changing position of the sound in its spatial map, the Doppler-like shift as the source moves, and it extrapolates forward in time. It models where the vole will be, and it aims at that. The calculation accounts for the owl's own flight time, the angle of attack, the depth of snow it will need to penetrate, the speed of the vole, and the likely variation in that speed. All of this happens in the second or two between the owl's decision to drop and its contact with the snow. In a brain the size of a walnut, without conscious mathematical reasoning, by instinct so refined it has become something that looks, functionally, like prediction. The dive. The physical act of the strike is its own extraordinary event. The great grey owl drops from its perch in near silence. The leading edge of its flight feathers are serrated at a microscopic level, breaking up the turbulence that normally produces sound when air passes over a wing's edge. The owl's flight is acoustically almost invisible. This is not an accident. A hunting owl that makes noise gives the prey a fraction of a second of warning. Evolution has eliminated that noise over millions of years, producing flight so quiet that the owl can continue processing the prey's sound during its approach without its own movement contaminating the acoustic environment. It is listening while it flies, updating its calculation in real time as it approaches. The final adjustment, the last-second correction of aim based on the most recent sound data, happens in the last meter before impact. And then the feet break through the snow. The talons spread to cover the maximum area, not gripping yet, covering. And when they contact the vole in the tunnel below, they close. The success rate of great grey owls hunting under snow in documented studies is approximately 75 to 80%. 3 out of 4 dives succeed. For a system operating entirely on sound, through an opaque medium on a moving target, predicting a future position, this is an almost unimaginable accuracy. The limits of human perception. To understand why this is extraordinary, it helps to understand what it requires of the brain that performs it. Human hearing localizes sound in 2 dimensions, left and right, roughly. We can determine horizontal direction with moderate accuracy. Our vertical sound localization is poor. We largely use visual context to assign vertical position to sounds. We cannot hear through snow. We cannot detect a sound source moving at vole speed through a tunnel below our feet. We cannot calculate the future position of that source and aim at it. We lack the asymmetric ear placement. We lack the facial disc. We lack the auditory cortex map. We lack the microsecond time difference processing. We are, by comparison, acoustically almost blind. The owl lives in a sound world so rich and detailed that it amounts to a completely different sensory reality from our own. When the owl sits in its pine tree looking at a snow-covered field, it does not see a featureless white surface. It hears a 3-dimensional map of everything moving beneath it. It hears the tunnel system, the individual animals, their speeds and directions and likely next positions. It is seeing the future of the field in sound. And then it drops toward a point in space that does not yet contain a vole. By the time it arrives, the vole is there. The science. The foundational research on owl auditory localization was conducted by Masakazu Konishi at Caltech beginning in the 1970s. His experiments with barn owls, a species with even more extreme ear asymmetry than the great grey, established the basic mechanism. Using soundproof chambers, high-speed cameras, and precisely positioned speakers, his team documented that owls could localize a sound source in complete darkness to within 1 to 2 degrees in both horizontal and vertical dimensions. For comparison, a human in the same test localizes horizontal sounds to within 3 to 4 degrees. Vertical localization in humans is essentially non-functional without visual reference. The follow-up research on great grey owls in field conditions in Canada and Scandinavia added the under-snow hunting documentation. Using accelerometers on prey animals, GPS tracking on owls, and slow-motion cameras, researchers mapped the complete sequence of a hunting strike. The finding that the owl aimed ahead of the sound source, that it was predicting rather than targeting, was published in 2011 and remains one of the most cited results in sensory ecology. The auditory cortex mapping, the discovery that the owl's brain contains a physical spatial map organized by sound, was established through electrode studies of barn owl neural tissue and confirmed in great grey owls by imaging studies in 2016. Together, these studies describe an animal that does not experience sound the way any other measured creature does. Every night. The great grey owl does this every night of its life. In the boreal forests of Canada, Alaska, Scandinavia, and Russia, the vast northern forests where it lives, winter means months of deep snow and near total darkness. For other predators, this is a period of difficulty, reduced hunting success, weight loss, range contraction. For the great grey owl, winter is simply winter. The snow does not hide the prey, the darkness does not reduce the accuracy, the cold does not affect the calculation. The owl sits in its tree, silent and still, its facial disc turned toward the field, its 3D auditory map updating continuously beneath the surface it is staring at. And when the map shows a vole at a predicted future position that the owl's flight time can reach, it drops through the cold air, in near silence, toward a point in the snow that does not yet contain what it is hunting, and arrives at the exact moment the vole does. The great grey owl has never taken a physics class. It has never studied Doppler equations or calculated flight trajectories or learned the acoustic properties of snow. It knows all of it. In a way that is deeper than knowing. A way that has no name in human language, because human language was built by creatures who cannot do what the owl does. We call it instinct. But instinct is just the word we use when we don't have a better one for cognitive capacity that arrived through evolution rather than education. The owl hunts the future every night, in a field full of snow and silence and nothing visible. And she is right.